moment area method, right? Another method to solve beam slope and deflection. When we did the introductory aspect of deflection and slope, I listed the method. I said we have moment area method, we have double integration method, we have Macaulay's method, and to the advanced level we have a lot of method, right? Now for this moment area method, there are things we must know before we start moment area method, right? Before we understand moment area method, there are some things we must be familiar with, right? And it's what we've done before. The first one is bending moment diagram. Basically you must know how to draw bending moment diagram. Given any type of beam, you must know how to draw your bending moment diagram. Let's recall. Given a beam, let's say you have a semi-supported beam, right? From here, what's the bending moment diagram of this semi-supported beam? The bending moment diagram of this semi-supported beam. So this is A, this is B, this is C. For my bending moment for this semi-supported beam, I have it like this, right? This is 0. This is 0. The idea is that bending moment starts with 0. Bending moment ends with 0. When we did strength of material there, we said bending moment starts with 0 and bending moment ends with 0. That's for if your beam, basically we have different type of beam. We have semi-supported beam, overhanging beam, cantilever beam. For cantilever beam, bending moment does not end with 0. You have a value at the fixed end. So this is what I'm saying. If this is your cantilever beam, this is A, this is B, this is B. So the bending moment of this cantilever beam, this is it. There's a value here. You have a value of bending moment here. Why this place is 0. So meaning you can take note for your semi-supported beam, overhanging beam, bending moment at the beginning and at the end you are 0. But for cantilever beam at the fixed end, you have a value of your bending moment. I get my point. But that's not what we are interested in. We are interested in moment area method. But I must say, you must understand this aspect, because that's what we are using. Typically, it's all about bending moment. Alright, now bending moment area method, as the name implies, it said moment area method. You are making use of moment, you are making use of area. The area in this case is the area of your bending moment. The area, this is your bending moment. This bending moment has its area. You can relate it to geometry. Let's say from here you have a right angle triangle. Of course, call this A, call this C, call this C prime. The area of ACC prime is what? 1/2 times the breadth times the height. So that's what it means. That's what it means by area. Any questions so far? So similarly, so in general, first thing first, draw your bending moment. Having drawn your bending moment, the area of the bending moment, that's what you are going to make use of. And what I'm saying now is actually all this that I've been saying since morning is actually the first theorem of moment area method. It is based on two theorems. Theorem 1 for slope, theorem 2 for deflection. That's the first aspect. Then for this moment, it's all about centroid. Meaning you must also be a master of your centroid. Seeing a shape, what is centroid? But you see how it works. But let's get started. Now, take down the first theorem of moment area method. The first theorem is used to find the slope. But let's take this theorem itself. The theorem states that the first theorem states that. Now, the thing is that by the time you understand this theorem, by the time you understand theorem 1, theorem 2, that's what you apply to any given question. All these things is all about you understanding the theorem. By the time you have solid understanding of this theorem, then exactly the same thing, that's what you implement to any given question. Are you getting me? Now, theorem 1. Theorem 1 states that the angle measured in radian, angle is measured in radian. So you are not saying the angle measured in radian between 2 points on the elastic curve of a beam between 2 points on the elastic curve of a beam is equals to the area under the M by EI diagram. Is equals to the area under the M by EI diagram. Now, what this M by EI diagram means is that bending moment diagram divided by EI. What's EI? Product of Young modulus and moment of inertia. That's it. Meaning, having drawn a bending moment, all the values at each point, divide all the value by EI. Now, this is what I'm saying. You know, this is my bending moment, right? Let's say this is my bending moment. Bending moment diagram. Now, I want to get bending moment diagram divided by EI. So what you are just going to do, this is still your bending moment. Initially, the value at this point 0. The value here is 0. The value here is what? PL. Let's say this is P kilonewton. L over 2, right? You know, this is your bending moment. At this point 0. At this point 0. At this point PL over 2. This is just bending moment diagram. But for M by EI diagram, meaning the bending moment diagram divided by EI. So in place of PL over 2, what you have here is PL over 2EI. And that's what we are saying. Now let's state the theorem again. The angle measured in radian between 2 points on the elastic curve of a beam is equal to the what? Area under the M by EI diagram. All those terms, they are key points in that definition. The first one is what? Angle measured in radian. The first one is angle. The second one is what? Elastic curve. Right? The third one is what? The point. Right? Now let's see what we are saying. What that theorem is saying. Let's see it. Therefore, theorem 2. Okay, let's see what theorem 1 is saying first. Then we move on to theorem 2. Let me say this. The absorption remains the same. You know, we derived a formula for double integration method, and we made a lot of absorption. We said from bending stresses to beam, we have this and that. So the absorption remains the same. They are still doing the same absorption here. Alright, let's say you have a beam. Let's say this is a beam. And this beam is loaded with some load. Let's say varying load. Uniformly varying load. UVL. No, I'm just using this for reference, just to explain. Let's say this is my beam. Yeah, we have UVL. UDL. What UDL means is that uniformly distributed load. UVL, uniformly varying load. Are you getting me? The difference is that for UDL, you know, what we know is UDL, meaning that given a beam, it will be loaded with UDL. Your beam can be loaded with UVL also. By UVL, what it means, this is it. Say this is a beam, and this beam, this is UDL, of course, right? Say this is 8 kilonewton per meter. Call this A, call this B, call this 2 meter, call this 3 meter, call the total length 5 meter. Now, at 2 meter, what is the intensity of your UDL? 8 kilonewton. The intensity, okay, 8 times 2, which is what? 16. But that's not what I'm asking. At 2 meter, the intensity is still what? 8 kilonewton. At 5 meter, what intensity? 8 kilonewton. At 3 meter, what intensity? 8 kilonewton. For a what? UDL. But for a UVL, the intensity varies. Just like the name implies, UVL. Meaning the intensity at 2 meter is different from the intensity at 3 meter, 4 meter, 5 meter. Are you getting me? So I'm just using this to explain.
Intensity force.
Yeah, magnitude. You mean magnitude. Intensity, magnitude. First acting on the beam, exactly. So from here, I'm just using this to explain. From here, I might load this beam with a UDL, a point load. But in this case, let me use UVL. And how do I know that this is UVL? It is not equal. It is not equal. Alright, now, of course, this is a semi-supported beam. True or false? True. Let's say this is C, this is D. And let's say this place is A, and this place is what? B. From here, let me draw the bending moment diagram of this beam. I want to draw the bending moment diagram, and I want to draw the elastic curve of this beam. Are you getting my point? Since I want to prove theorem 1, we want to see what this theorem 1 is saying. the mathematical expression behind theorem 1. It's not as if a theorem is just stated. There's a mathematical expression for it. Now, that mathematical expression, we say, given this beam, let's say this is a beam, call this place C, call this place B, say this is A and this is B, right? Now, let's get the elastic curve of this beam and get we get the elastic curve, get the bending moment diagram, and get the what? Bending moment diagram divided by EI, meaning M by EI diagram. Alright, let's say you have this. From here, we are familiar with this, right? This is my line. The elastic curve, my beam will deflect in this nature. You know, the idea of deflection, from when we did double integration method, we said when your beam is loaded with a point load, or whatsoever the load might be, is going to what? Deflect. And the difference between the axis of this beam, of course, this is the axis of your beam, right? And this is the what? Elastic curve. Are you getting me? Yes. So the difference between this axis and the elastic curve is what we call what? Deflection. Right? Now, from here, this is my elastic curve, right? And why am I showing the elastic curve? Because from that theorem, we made mention of what? Elastic curve. Okay, this is C, right? This is what? D. This is what? A. This is what? B. The what? The tangent, the angle measured in radian between two, that definition is not completed, between the tangent of any 2 points on the elastic curve of a beam, between the tangent of any 2 points on the elastic curve of a beam, between the tangent of any 2 points on the elastic curve of a beam, meaning your slope will occur where? At the between two tangents of your point on the beam. Are you getting me? Now, let's use point A and point B. Meaning the slope, I'm having a slope, right? But what I'm going to indicate the slope is between these two tangents, between the tangent of A and the tangent of B. Are you getting me? What if I'm using BD? Meaning the slope becomes what? The tangent, the slope will occur between the tangent of B and the tangent of D. What if it is C and A? It will occur between the tangent of C and the tangent of what? A. So this is the elastic curve. Now let's draw the tangent. What tangent means is that we can relate it mathematically. Say you have a curve, a straight line drawn to your curve is what we call tangent. If this is a curve, this line, this straight line, say this is point B, meaning this is the tangent at point B. Then you can relate this to trigonometry, saying you have an angle, right? So this angle is what? Theta B. Why is it theta B? Because it is at point B. What if we have A here? Let's say we have this. Let's say you have something like this. Of course, you have an angle here too, right? This angle is what? Theta A. So meaning any straight line drawn with respect to your curve, you have an angle there. So that is, I'm using this guy to explain now. Let's say you have a tangent drawn. This is what? Tan A. The tangent drawn at A. This is what? This is what? Tan B. Now go back to that theorem. The theorem states that the angle measured between what? The angle measured in radian between the tangent of any 2 points on the elastic curve of a beam is equal to the area under the M by EI diagram. Meaning this is tangent for B, this is tangent for A. Meaning you have an angle. The angle between the tangent of any 2 points. The any 2 points now is A and B. The point in this case is A and B. This is tangent of B, this is tangent of A. Meaning between point B and A, you have an angle. This and this, there's an angle. So this angle is called theta B A. This angle is called theta A slash B rather. Meaning the angle B makes with respect to A. Similarly, the angle A makes with respect to B. You know, normally, this is moment theorem method. You know, of course, I can solve the value of angle here. Let's say you are given a question under double integration method. You know, I can find the slope at A, find the slope at B, right? Now, that's what we are saying here. that the slope at B is denoted as what? Theta B slash A. The slope at A is denoted as what? Theta A slash A slash B. Meaning what this guy means is that theta B slash A is equals to what? Theta B. Theta B slash A is equals to what? Theta B. But in this case, how you write it is that theta B slash A is equals to theta B minus theta A. Do you understand? Theta B minus theta A, meaning the slope at A at B minus the slope at A. Depending on the point. Are you getting me? The point in this case is what? B to A. Meaning the answer you get is for what? Theta B. Meaning the slope that will occur at this point. Now let's use this. What if I have theta A slash theta B? That's what? Theta A minus theta B. But I know that the answer that I'm going to get is what? Theta A. Meaning the slope at A. And that's what we are saying. Alright, now, but from here, this is just the relationship between the elastic curve and the tangent. Now, this area that we are talking about, what does this area mean? Meaning the M by AI diagram that we are saying. Now, from here, let me draw my bending moment. I will draw my M by AI diagram directly. Do you know why? Because the idea is that bending M by AI diagram simply means your bending moment divided by EI. So let's say that this is my bending moment diagram. So this is X, this is Y. From here, I'm just doing an assumption since there's no magnitude for this load. So we are just using it to explain. All we are doing here is hypothetical. We are just using it to explain. Now from here, let me say this is my bending moment diagram. Are you getting me? Let me say this is my bending moment diagram. You know, at this point, we have the value of moment, right? At this point, we have the value of moment. At this point, 0. At this point, 0. And for this guy here, this is what? Okay, let's shade this guy. Let's shade this. Call this 1. Call this 2. Call this what? 3. Now, you answer that question by yourself. Now, with Theorem 1, you know, yeah, you can get the area of figure 1. You can get the area of figure 2, and you can get the what area of figure 3, right? But in this case, this particular slope is equals to the area of this diagram. We don't know yet. Is it figure 1? Is it figure 2? Is it figure 3? Are you getting me? Now, this is the M by EI diagram. This is the M by EI diagram. Let's say you've gotten the moment at each point. You just divided all through by what? EI. Now, bring that Theorem 1. So you reading that Theorem 1, what I want you to do for me is to tell me the slope, this angle, the area this slope will be equals to. Is it figure 1, is it figure 2, or figure 3? That's why I'm telling you to read the theorem. So read the theorem for me now. The angle measured in radian between the tangent of any 2 points on the elastic curve of a beam
is equal to the area
under the M by EI diagram. Now check, this is the M by EI diagram. So what is the area? Is it figure 1, figure 2, or figure 3? Check the board. Is it figure 1, figure 2, or figure 3? This guy here, the area, this slope is equals to a particular area, and the area it is equals to what? The area that is under the M by EI diagram. Meaning, the place you have your slope, the place your slope occur, the area under that place, under that 2 points, that the figure you have there, the area of the figure you have there, that becomes the slope. Now check, is it 1, is it 2, is it 3? 2. Are you getting the point? It is 2 because you are between what? A and B. You are between point A and B. Point A and B, tracing it down. The area here is figure 2. What if it is C and A? The area is what? 1. If it is B and D, the area is what? 3. And that is how it works. Do you understand? Yeah. So that's what that theorem is saying. You understanding theorem, I believe, given any question, you just relate it to it. And that's it. That's Theorem 1. You don't understand Theorem 1 now?
Yes.
So what it means is that given any type of question, as far as you want to calculate the slope, your first task, draw the elastic curve. Having drawn the elastic curve, draw the tangent, relate the angles between that tangent. Once you are done with that, draw your head by EI diagram. So the area under the slope you are calculating, between the point that you are calculating the slope, that will be the area. Then use the formula for that particular area. You know, when you draw your beam, the area here might be a right angle triangle. The area here might be a parabolic shape. The area here might be a rectangle. So depending on the area, your 2 points it falls on. You get? That's what you use. So that's how it works. That's theorem 1. Generally, what it means is that from here, this is the relationship between the point on your elastic curve. I already know that the slope between them is equal to the area under the M by AI diagram, right? Now, let's see the mathematical formula for it. This is the formula. Theta B minus theta A is equals to integral theta A theta B M by EI dx. Are you with me? This is the formula. Now let's see how this formula is being derived. It's being derived. Now from here, this is how it works. From here, let's take an elemental portion out of this total length of the beam. The absorption remain the same. You know, from here, this is the bending moment diagram. This is EI diagram, right? So the absorption remain the same. So we're doing some absorption here, but take note, it is still the same. It's the same as the previous absorption where we derive double integration formula. Okay, now from here we are doing an absorption, and this absorption is that we are taking an elemental portion out of this length of the beam. Meaning, say this is your beam, this is your beam, this is A, this is C, this is D. Okay, let's say this is just a beam. Let's say this is A, this is B, this is a semi-supported beam, right? Now, you are taking an elemental portion. Are you with me? This elemental portion, call it the X. Then, by the time this beam is loaded, let's say this beam has been loaded with a uniformly varying load, or whatever the load might be, any type of load, load it with point load, load it with a UDL, load it with a UVL. You are still saying the same thing. Now I'm loading this beam with a UVL, right? Of course, this beam will deflect. So by the time this beam deflects, I'll be having something of this nature. Meaning this load has caused this beam to deflect. This is A, this is B. Is that correct? And this is still what? The X. What I have here, say this is case 1, and this is what? Case 2. For case 1, unloaded beam. This is for case 1. This is it. For case 2, my beam has been deflected. Meaning, this beam, this elemental portion, will also deflect. Is that correct? This is where we are going back. We want to see how this formula is being derived. Now, from here, let's take this elemental portion. We are only interested in this. Are you with me? We are only interested in this elemental portion, which is what? The X. So let's bring out the X. I'm bringing out the X, right? So let me have this line. From here, by theorem 1, we said the target between any 2 points, the angle measured in radian between the target of any 2 points is equal to what? The area under the M by EI diagram. And we said that the formula, right? Let's see how that formula is being derived. So this is the first, say this is the first point, this is the second point. Then this point, let's say this is point A, this is point B. This point A and B, they have their respective target, right? So the angle here, we have an angle here, right? We are just replicating what we learned here. What we have here, that's what we are replicating. So the angle here, call it the theta. Are you getting me? The angle here, call it what? The theta. Then extend this guy up to this extent. Of course, you have an angle here too.
But why is the angle not that?
This place, you might use the angle here too. You also have an angle here. The angle here is the same angle here. We are just using these two as reference. We are taking one to just explain. So if we have an angle here, extend this guy perpendicular line, you have an angle here too. So the angle here, geometrically, this angle is equals to this angle. So this is also the theta. Then this is the radius of curvature. I said the absorption remains the same. For the first one, we have radius of curvature. When we this double integration method, so that's what we are still using here. Then this is the x. We also took an elemental portion for the first one too. That was the x, but the type of x it is, this is it, the x. So it's still the same concept. The absorption remains the same. Then from here, let's bring something like this out. This is the theta, this is the x, and this is r. Abi? Then I'm using what? Tan theta is equals to opposite over adjacent. This is my opposite, this is my adjacent, right? This is opposite, this is adjacent, and this is hypotenuse. Anywhere your angle is facing is the opposite. Anywhere the angle of inclination is facing is the opposite. So this will now be what? Tan the theta is equals to what? Opposite, which is what? The x, divided by adjacent, which is what? R. We said absorption remains the same. In this case, you assume that the angle is what? Very small angle. And if the angle is small, what will happen? Call this equation 1. If the angle is small, meaning equation 1 can be written as what? The theta is equals to the x over r. Call this equation 2. You see that we are still in the same absorption. So that's it, if you can remember. From equation 2, we call from flexure equation, bending stresses in beam, from flexure equation, meaning bending stresses in beam, m by I is equals to E over R is equals to stress over Y. M over I is equals to E over R is equals to stress over Y. Using this relation, right? Using M over I equals to E over R. Make 1 over R the subject of the formula. It implies that 1 over R is equals to what? M over EI. This is what we've done before. In double integration method, we've done this before. So you can watch the video on that. We've done this before in double integration method. Meaning from equation 2, you have that the theta is equals to 1 over R times the x. Right? Yeah. The theta from equation 2, the theta is equals to what? The x over the R, which is the same thing as this. And we already found 1 over R to be M by EI. So substitute. What do you have? M over EI. Therefore, the theta is equals to what? M over EI dx. And where is the theta coming from? This angle. Meaning that any angle formed or obtained between your tangent, this is the formula. Are you getting me? Meaning that any angle, we've seen it graphically now, right? But mathematical proof to it, that's what we just did here. So in general, what it means is that any angle formed between the tangents of any 2 points, this is the formula. Any angle formed between the tangents of any 2 points, this is the formula. Are you with me? And in this case, the angle is what? The theta. And we end up getting the theta to be M by EI dx. So this is the formula. So given any question, this is the formula. But you can modify this formula. Now this will bring us to integral calculus. From integration, when you have something like this, between the tangent of any 2 points, you want to find the slope, right? The angle formed between the tangent of any 2 points, this is the formula. Now let's say the point now is between A and B. Let's say between point A and point B. Now this formula, you can write it as from between point A and B, you can write it as theta B to A is equals to theta B minus theta A, which is equals to integral theta A theta B M by EI dx. The question is, from here, how do you got this? We said if the point is between A and B, from here, this is what we have. And this is what I just did here, implementing the idea of calculus, right? Integral calculus. You know, let's say you have something of this nature. Let's say you have something of this nature. If this is y, this is x. So this is y equals to f of x. Then this is your area. This is xa. This is xb. Is that correct? From here, to get this area, area is equals to what? Integral xa, xb, right? Y dx. Y dx. This thing from integral calculus. Let's say you have this plane, 1x. This is your curve. This is the area. Right? Now, implementing that same idea to these 2 points. This first point, what do you have here? Theta A. This first point, what do you have here? Theta B. So, applying this logic, applying this idea, y, this is m by ei. This is the point we are talking about now. This is what? Theta A. This is what? Theta B. I'm interested in this area, right? I'm interested in this area. Applying same idea, the area here becomes what? Area is equals to what? Integral theta A, theta B. Y here, this axis, right? What do you have here? M by ei dx. And you can relate that dx from here. You know, we took an elemental portion here, meaning you are saying from here, this is dx. So you can trace this guy up to this level. Right? This is the what? The x. Area, length times breadth. This is the what? Breadth times height. This is the breadth, the x. This is the height.
Okay, so you can say we should look for the x.
Huh?
Are they going to say we should look for the x?
No. Just understand. I get me, just understand. But I'm just taking it back to this. But this is the formula. I get me. Meaning area is equals to integral theta A, theta B, m by ei dx. What if the point is C and D? What if the point is C and D? That will be what? Theta area is equals to what? Integral theta C, theta D, m by ei dx. But in this case, it is what? Theta B minus theta what? A equals to this. Similarly, this is also what? Theta D minus theta C is equals to this. So can you now relate this formula now to this? This formula says that generally the angle between any two tangents of a point, this is the formula. Now in this case, between B and A, between B to A, from here this formula between B to A, he said theta, from what we explained before, we said theta B to A, and it is read as theta B minus theta A. The angle that theta B makes with respect to theta A, meaning theta B minus theta A, this is the formula. So this guy here means the theta. Then m by ei dx, this is it. Likewise, if it is between D and C. So that's how it works.
You can first write this formula outside.
You don't really need to write formula. So all this one is just like mathematical proof. But just so that we solve the question. The way we solve that question, you can use this formula to direct. There's a method I saw that they make use of this formula. They integrated the value exactly. They integrated the value and they integrate with respect to x. And they introduce the limit and they got the answer. This formula, you can make use of this formula and you can make use of the graphical method. So this formula, this moment theorem method is a semi-graphical method. Meaning you do graph, you do numerical calculations.
So let's say you are done with this.
Okay.
So which one will be numerical calculation?
This is like more of like numerical calculation.
So
From here. No. You just want. All this one is like proof.